This is exercise 4. And here we are given a curve K, which is the set of points x, y, z, where x minus 1 squared plus y squared is equal to 1, and z is equal to 2 minus x. And also we are given a vector field x, y, z, which is equal to y, z, x. So here the problem is that we want to verify Stokes' theorem in this special case. That is, we're going to compute the circulation directly using the tangential curve integral, but we're also going to use Stokes' theorem and calculate the flux of this vector field through a spanning surface for the curve K. So what we need in order to get started is that we need a parametric representation of K. And if you look at the first part defining K, you can see that in the XY plane, this is a circle centered at 1, 0 and with radius 1. And we know how to do this. We have, say, if we use a parameter t, then we can get the two first coordinates as cosine t plus 1, because it's centered in 1, 0, and the second coordinate will be then sine of t, and the third coordinate we get from the second relation defining K, that is z is equal to 2 minus x, so I simply write 2 minus x, and that would be 2 minus 1, that is 1, and then minus cosine of t. So here I have the parametric representation for the curve K. And now it's fairly easy to compute the circulation. I write here the circulation around K of the vector field times a unit vector d mu. And when you unfold this in terms of your parametric representation, then you have, this is the integral from minus pi to pi. T runs from minus pi to pi. And then you need your vector field, and your vector field is y, which is sine t, and then it is z, which is 1 minus cosine t, and then finally it is x, which is 1 plus cosine t. And you need to dot this with, with the tangent vector, which is the derivative of r with respect to t. So you get minus sine t, you get cosine t, and then finally you get you get, when you differentiate, you get sine of t as the first third coordinate. So this will be the integral from minus pi to pi. And then when you compute it, you get minus sine squared of t. And then you get plus cosine t minus cosine squared of t. And then you get plus sine of t, and then plus sine of g cosine t. Again, when you integrate, say, cosine and sine over a period, then the integral is 0. And you can rewrite sine t, cosine t in terms of the double argument. It's 1/2 sine of 2t. So this will also be integrated across the period. And minus sine squared of t minus cosine squared of t, that is minus 1. So this will be equal to the integral of minus 1 dt. And this is minus 2 pi. Now, let's try to solve to solve the problem using Stokes' theorem. I could write here now using Stokes. And then you need a parametric representation of your curve K. Let me just sketch the curve here. You have and then X, Y, Z, and you have, it's the interface between a cylinder of unit radius and then a plane set equal to, so this is 2 here and then 2 here, so you have a plane here. And imagine that this is a plane that runs like this. And and you have the plane here, and so it will be a curve. The curve will be like this. So it will be an ellipse. And we have written the parametric representation for the boundary. So in order to write, say, we want to take the simplest possible filling surface for this boundary, and this will be just this elliptic disk that you get like this. And you get this by just using the disk in the XY plane. Let me write this down. Now you have 2 parameters in order to I could write it here, R of u comma v. And this will be, it will be u cosine v and then u sine v. But, or plus 1 because it's displaced 1 in the positive x direction. And then again, you have that the z coordinate is 2 minus x. So this will be 2 minus x. So this will be 1 minus u cosine v. So, and u will be equal or will be in the interval from 0 to 1. And v will be in the interval from minus pi to pi. So this is the parametric representation. And when you calculate, say, the normal vector, then you get r prime u cross r prime v. And this is simply cosine v sine v, when you take the derivative with respect to u, and then minus cosine v. And you should cross that with the r derivative, and this will be minus u sine v, and then it will be u cosine v, and then it will finally be u plus u sine v. And when you calculate this, you get u 0 u. And if you want to look at the direction, let me draw this in red. At the direction here, you get that it is pointing in that direction here. So this will be the normal vector. And when you calculate the flux, this is times the v vector, you get dx dy dz cross y z x. And when you compute this, you get minus 1, minus 1, minus 1. So it's a constant vector. And then you can calculate the circulation as minus pi to pi, the interval from 0 to 1. And then this flux here times the normal vector, and then du dv. And this will be, again, this interval. And then you get minus 1, minus 1, minus 1. And then dotted with u 0 u. du dv. So you get that this will be the integral from minus pi to pi, from 0 to 1. And then this dot product will be minus 2u du dv. And the interval of minus 2u, this is simply minus u squared. from 0 to 1, and then you should integrate from minus pi to pi of, and you should integrate with respect to b. Now, the lower limit doesn't contribute, so there's a minus 1 from the upper limit, and then it will be minus the interval length in the v direction, so this will be minus 2 pi. So you see, when you use Stokes, you get the same result as if you have calculated the circulation directly. Okay.